everyone to join. We will start within the next few seconds. Good afternoon, everyone. A very warm welcome to all our attendees joining us from across the country. We are absolutely thrilled to have you here today for this highly anticipated session, Accelerating Automotive AI with MATLAB, faster simulations with ROM and efficient embedded development. This special webinar is presented by MathWorks and proudly powered by Pro MFG Media. The automotive landscape is evolving faster than ever. Today, we are diving deep into how engineering teams can bridge that massive gap between high-fidelity simulations and real-time deployment. Whether you're looking to accelerate your simulation workflows without losing accuracy, deploy AI efficiently on edge systems, or explore how Gen AI is changing the game for engineering productivity, you are exactly where you need to be. Our speakers for today are Kaustubh Shirke and Piyush Pankaj from MathWorks. The discussion will be facilitated by my colleague, Manish Kulkarni, who is a director at Pro MFG Media.
Hello, good evening, everyone. Pleasure to be here and looking forward to an insightful session.
We have a packed and an incredibly insightful session ahead of us. But before we dive in, we will have a dedicated Q&A session at the end. So as the speakers are presenting, please feel free to drop your questions into the Q&A box at any time. Don't hold them back. We want to get to as many of your technical queries as possible. And here is an extra incentive for you. We are hosting a live lucky draw at the conclusion of this webinar. A few lucky winners from our audience will be walking away with some exciting prizes. So make sure you stick right until the final wrap-up. Now to guide us through these cutting-edge workflows, we have with us Kaustubh Shirke and Piyush Pankaj. They bring years of deep technical expertise in automotive systems, AI deployment, and advanced simulation engineering. Kaustubh Shirke is a principal application engineer at MathWorks, specializing in AI-based workflows for the engineering applications, with a strong emphasis on automotive and industrial systems. With close to a decade of experience, he has worked extensively with leading automotive OEMs and suppliers to develop AI-enabled workflows for advanced engineering applications. Kaustubh's core expertise spans virtual sensor development, reduced order modeling for accelerating CAE simulations, predictive maintenance, anomaly detection, and embedded AI deployment on production ECUs. He also plays a key role in helping organizations integrate AI into traditional model-based design workflows, enabling faster development cycles while maintaining engineering rigor, safety, and performance standards. Prior to joining MathWorks, Kaustubh contributed to AI-driven innovations in automotive applications, working with organizations such as Cummins and Mercedes-Benz Research and Development, where he helped integrate AI models into production engineering workflows. Kaustubh holds a bachelor's degree in mechanical engineering and a master's degree in mechatronics from the University of Duisburg-Essen, Germany. Piyush Pankaj is a senior team lead for AI and technical computing products at MathWorks, with 15 years of experience at the intersection of mechanical engineering, aerospace, and data analytics, a rare combination that shapes his approach to solving complex engineering challenges. He began his career in the aviation industry, contributing to the design, testing, and certification of aircraft engines, and earning 25 patents in jet propulsion technologies and prognostic health monitoring. At MathWorks, Piyush collaborates with leading organizations in automotive, aerospace, and industrial automation to deploy AI, machine learning, and advanced analytics at scale. Holding a master's degree in advanced mechanical engineering from the University of Sussex, UK, Piyush is recognized for bridging deep domain expertise with emerging AI practices to drive digital transformation and intelligent system deployment. I now invite Kaustubh to provide a brief overview of MathWorks, its products, and the role MathWorks plays in the AI domain. Over to you, Kaustubh.
Yeah. Thanks, Bianca, Manish, and Sanjay sir, as well as thank you to Pro MFG Media team for providing us the opportunity to talk about this new topic, that is the AI in automotive. Here we maybe walk you through the different AI applications, their development, deployment, how you can deploy the models maybe on the edge, on the cloud. Before jumping to that, maybe I will just maybe try to give the overall overview, right? How the what exactly MathWorks or MATLAB offers in the space of the AI for engineering. So basically, we normally offer maybe two main products or solutions. One is the MATLAB. We have been creating a MATLAB sibling to help engineers, science to do their technical work best, right? So first is the MATLAB, which is nothing but the programming language or programming environment for algorithm development, data analysis, signal processing, and the numerical computation, right? Then we have Simulink, which is maybe block diagram based environment, which is built for the building some models, modeling and simulation of the different engineering subsystems, right? So you can maybe reduce the prototype before maybe going for the production. And on the top of that, we also provide a lot of domain specific toolboxes, maybe predictive maintenance, image processing, computer vision, and so on, right? So we have maybe around 130 different additional products for specialized tasks. For example, computer vision, maybe the medical, pharma, and so on, right? So this is about the MathWorks as well as the products. Now we are seeing the applications of AI with our software across the multiple industries. Maybe you can maybe see from maybe aerospace, automotive to biotech, energy productions, finance, medical devices, as well as the railway systems, right? And we maybe try to incorporate feedback, learning, and feature requests from the customers in all these industries, right? And also we also see the parallel across many of the industries that our technical teams share those learnings with you, right? So we learn maybe from interaction with the different industries, and we try to establish some workflows which might benefit from to the customers from all these industries, right? But today maybe we'll be more focusing on the automotive applications, automotive use case, right? Now, before jumping to the use case, maybe some might be very new to AI, some might be at intermediate level, but I just maybe give the little bit high level overview of the what is AI. So we have the artificial intelligence, which is the main bucket. Under that, we have the machine learning. Normally, we have some inputs, output. We train some model, and that machine learning try to estimate some function, some empirical formula where we can give new inputs and we get the new output, right? And deep learning, we might say that it is the advanced version of the machine learning, where we have a lot of inputs and we give the input and we get the output. Machine learning, normally we need to have the right inputs. For example, suppose you want to predict maybe the fuel efficiency of your engine. We need to know what are the right inputs. We can go ahead with the machine learning. But in case you don't know which are the right inputs, we have a lot of inputs, maybe 20, 30 inputs. Maybe deep learning has capability to identify as well as leverage the right inputs, right? Machine learning mostly used for the numerical data. Deep learning, in case it can work also numerical time-dependent data as well as the image, audio, video data, right? Based on the use case, based on for which application you want to use the AI, we can take a call whether you have to go with the machine learning or maybe deep learning. Piyush will talk more about from the MathWorks perspective applications of the ML and DL. Right? Let me again recall what I discussed on the previous slide. If you have maybe the domain knowledge, you need to have the domain knowledge to choose the right inputs. Suppose here I want to train some model which can classify maybe whether it is a truck, bicycle, or car. We need to have the right features. Right features means right input. Maybe the size of that, maybe the weight of the vehicle or the engine of the vehicle. Based on that, it will understand to classify whether under truck, car, or maybe the different vehicle. Right? We need to have the domain knowledge for that. In case you don't have domain knowledge, but you have a lot of data, then maybe you can go ahead with the deep learning. So you have a lot of features, you have a lot of input features. You don't know which are the right one for the classification. In that case, you can go ahead with the deep learning. This is just maybe quick differentiation, which can help you when to choose which kind of algorithm models, right? Whether you have to go with the ML or maybe DL, right? Now, before just moving ahead, I would like to maybe raise one poll. just to understand the maybe your journey with respect to AI/ML, whether you are beginner, whether you already implemented the AI/ML for a specific task, or maybe you want to explore more, right? We'll just pause here for maybe 10 seconds, and then we will move ahead. Okay. All right. Maybe also I would like to ask maybe first question to Piyush, that you have been working with a lot of automotive customers on the different projects. Sometimes you have worked with the data scientists, sometimes you have with the domain experts who don't have the AI knowledge. Maybe based on your experience, which are the maybe top 5 or maybe top 4 use cases you see when it comes to AI in automotive, right? That can give some insights to our audience. Over to you,
Sure.
Piyush.
Thank you, Kaustav, for the question. And so basically, I would like to bring your insights into the different type of applications that we see under automotive industry vertical. So first, I have to share with you is the fleet data analytics. And at the bottom, you will see that MathWorks also as a company has worked with multiple customers across the globe. So for example, Daimler and Honda have used our fleet analytics capabilities in the product line to basically analyze how multiple assets are doing in the fleet, at the same time how individual assets are also doing. So you can query these individual assets for how they are performing with respect to health or with respect to fuel economy, etc. Second application area is predictive maintenance, or we also call this as anomaly detection, fault classification, or remaining useful life kind of application areas, where we have also worked with John Deere and TCS as an organization to basically build on data lake kind of applications as well as anomaly detection workflows. Next up, I have virtual sensor modeling. This application area, as the name suggests, you are basically building a surrogate AI model based on some simulation model, or it could be some test bed related data that you have collected. But the goal is to replace an already existing sensor in the field with the AI based sensor, or there could be places where you cannot actually put the sensor. So in those applications, you actually put this virtual sensor. Some of the application areas could be estimating the NOx emission out of your engine, and that is where we had collaborated with Stellantis and Renault as companies to basically cover these areas. Then next up is reduced order modeling. Now, in this particular application area, your goal could be different depending upon whether you are dealing with actual complex physical data, or you want to reduce the simulation time of a numerical model where you could be dealing with 2-dimensional, 3-dimensional kind of high fidelity models. So these kind of application areas help you train an AI surrogate model and replace some of the subsystems in your numerical model with the AI based surrogate. So here we had worked with Cummins, a couple of years back to basically implement a deep learning based solution. Next up, we have got reinforcement learning. Now, in reinforcement learning, this is a different type of category, because reinforcement learning is an area where if your system is very dynamic, let's say for example, in order to predict emissions, it could be a transient behavior of the system which will change with respect to environment. So in those cases, you would need a reinforcement learning model which can understand by interacting with the environment. You do not need a lot of data for training a reinforcement learning model agents. So that is where we had worked with Vitesco on NOx emission kind of examples. And then the last is product design optimization, where your goal is, after you have built an AI surrogate model, how do you use it to understand the sweet spot in your complex system where multiple design requirements can be met. And these kind of workflows could be heavily important for certification standards also that we are looking into. So here we have worked with companies like TWT, GmbH, which is a German automotive company, and Subaru. So at a high level, I have covered you some examples, Costa, which relates to sensor-based modeling. But although I have not touched on vision applications, but we also have solutions around those.
Yes, Piyush. Yeah, Piyush, thanks. You maybe try to touch the different applications of AI in automotive. Some might be helpful for maybe development. Some might be going directly to production. Maybe you might be deploying maybe on the hardware microcontrollers or maybe on the cloud, right? Maybe we have maybe in today's session, why don't you maybe deep dive into one of the applications, right? Maybe reduced order modeling, right? Which will be mostly important for
Sure.
engineers who are working in simulation domain.
Yeah, sure. So reduced order modeling, let's first understand what this application area is all about. So when we, mention about reduced order modeling, your ultimate goal is to take a high fidelity model and convert it into a low fidelity model, which approximately is giving you the similar set of results that you would actually get from a high fidelity model. And the benefit could be, different. Some people we have seen use the reduced order modeling approach for speeding up a desktop level simulation where numerical softwares are taking large amount of time. Some people are interested in doing hardware in loop testing, or they want to control the design of a controller, right? And in some cases you could have some complex physics which your model is not able to cover. So in those cases you want to build reduced order models based on some test data as well, and replace some sub system in your higher fidelity model with a AI based reduced order model. So, before going deep into this workflow, I would like to introduce this particular user story to you, which I also mentioned on the previous slide, because this is an example where, while working with TWT GmbH, which is German automotive company, they wanted to design a suspension system of the vehicle, and they had multiple parameters and high fidelity model over there as well. And they also wanted to understand how they can actually predict the performance of the suspension system using multiple parameters. And later down the line, they also used it for doing design optimization of their suspension system. But before doing that, they were actually able to train pretty accurate deep learning models based on multiple parameters, and the output of the suspension system could be acceleration or the velocity in different coordinate system basically. So this is where our tools were actually used, and they got pretty good results. Ultimately, after applying optimization, they were actually able to reduce multiple days of works into minutes of work. Right. So with that, I will actually launch a poll to understand, for which of your applications you are actually looking to use reduced order modeling. Do you want to just speed up the simulation time, or are you looking to tune any of the design parameters in your numerical models, or you want to explore the feasible design space ultimately, or maybe if you're interested in running what if scenarios, or perform hardware in loop testing, or you want to leverage ROM for control design. Right, so we'll spend maybe 10 to 15 seconds over here, giving you enough time to opt the suitable option over here. All right. I hope you got the chance to vote in on one of the options over here. Now, moving forward, let's get deeper into the workflow. What exactly, how do we exactly use reduced order modeling? So first step in reduced order modeling is to generate some synthetic data. And your data generation could come from either MATLAB or Simulink, where you may have the numerical models, or your numerical models could exist in different third-party softwares as well. Now, once you have the data and you also have done some kind of data pre-processing, the next step is basically model training, where the model training will be done on the design of experiments data. You could choose from machine learning or deep learning kind of models. After you have trained one model or multiple model for the same design outcome, then you would actually try to validate which of the reduced order models that you have trained is working with respect to your scenario or with respect to your design requirements. And then lastly, you want to export this particular model to replace a particular subsystem in your larger fidelity model. Right. Next up, I want to show you this particular example of Simulink, model, which is pretty detailed automotive model that we have got. You have got passenger car, you have got controllers, then you have the driver, basically, which is operating on a particular duty cycle. So you have the road conditions coming in, you have the simulated driver environment, etc. And to go deeper into this particular passenger car consists of engine, model, as well as the transmission system, etc. But the goal over here is to ultimately take a lot of inputs and from this high fidelity model, and then go into building a reduced order model to basically get a much faster simulation. So in this example, we have got 4 different inputs, which are engine speed, ignition timing, throttle position, and wastegate valve. And the output that we recorded, from the simulation model is the engine torque, right? And the goal then is to build an AI model on top of it. Now at MathWorks, we like to break this this whole journey into four major buckets. The first is data preparation, where I spoke about data generation in the previous slide. Then AI modeling. Also, there are multiple models to choose from. I'll talk about that in a couple of minutes. And then once you are done with the model training and testing the model, you want to test this model in while integrating it with the larger subsystem, right? And then once you have done that, you want to maybe take it for deployment on embedded or cloud, assets that you may have, right? So how do we get started on generating the data for our AI model? So this is where we use a technique called design of experiments. And the whole goal over here is to use your existing high fidelity simulation model to generate some synthetic data for you, because you understand which of the parameters would be something that you want to control, and that is where bringing your domain expertise is highly critical in this kind of application areas, because your engine or your overall vehicle might have hundreds of parameters, but your domain expertise will let you choose among the right parameters. Now, for four input parameters that we chose, and the output parameter was designed or the engine torque. Now, the goal is, instead of just using some conventional design sampling methods like full factorial, we have multiple sampling methods in MATLAB. Now, in this study, we use something called as Latin hypercube, sampling, because that is where we have the control on how many number of simulations we can actually run. Now, the next question, which is important, is we have a bunch of machine learning models, deep learning models, etc. How do I choose which is the right set of models for my application area? So that is where, if you look at deep learning models or a static model fitting or machine learning model, then on the dynamic side, you have nonlinear arcs model, linear parameter varying model, and on the projection side also multiple models are there. So how do I decide as a domain expert that which model is suited for my category or for my application? Right. So that is where I would like to introduce multiple interactive UI applications in MATLAB, which basically has a low code, workflow where you are not necessarily writing a lot of code. At least with the model training on the machine learning side, you do not have to write any code. And then on the deep learning side, some code may be required, but the heavy lifting is being done with these interactive applications. So let me show you this particular video where I would like to show you that how the data looked like for my application. So let's say, right now I'm showing you a case for a steady state analysis. Now, in this case, I had multiple columns for input data and then, column for the output data. Now, once this particular data table is loaded into your memory, then we navigate to our machine learning and deep learning segment in the app gallery, and then we launch up an application called Regression Learner. Now, once this regression learner app is launched, we start defining a new session over here. And in under new session, you can bring in your data into the memory of this application. So we are embedding the data over here. We select what is the response that we want to train the AI model for, and what are the predictors. And then we import the data. You can split the data also there itself into train and test. And once the data is actually imported, you have multiple features within this application, where the important one is feature selection, where you can conduct different statistical tests. Now, in this case, we have just 4 parameters, so we may not be reducing any data over here or any dimension over here. But imagine if you have hundreds of variables, then you can explore this step also and reduce the number of variables that you are looking for. Then we have got a drop-down menu where almost 30 different models are there in our latest version on the ML. And then you can choose as a beginner or as an experienced data scientist also, you can choose which models do you want to train, or you can go ahead with training all the models which are available for quickly being trained. And that is what I'm doing over here. Now, at the click of a button, you would see that multiple models are getting trained on my device using parallel computing support as well. And that is where MATLAB starts to highlight which models are actually performing better on your data. Then you can evaluate, the R squared value, RMSE value, mean absolute percentage error kind of values for your understanding of how your model has been trained on the response. So this is a curve on, showing actual versus predicted data. On the, x-axis was the true data and y was the predicted data. And at the click of a button, you can also generate a MATLAB function out of it, so that the next time you want to train this model, you don't have to open the app and import the data back again. You can just run this particular function with the new data. So that is where, this kind of no code workflow helps you a lot. And then, moving forward, when we are, done with training multiple machine learning models, you can choose one and then export this particular model to be embedded into Simulink, right, which is our simulation environment. Now here, you can have a block representation which is showing you the model integration, and then we can test out, if the input data is being transmitted properly and the output is expected, as per the behavior, right? So next up is another example on the deep learning segment. Now, deep learning is where if your system is getting more complex, you can train something called as neural networks. Now, over here, you would see from the app gallery, we are opening an app called Deep Network Designer. Once we open this particular app, you can load up, some transfer learning models if you are working on vision applications and all, or if you are working on sensor applications, then sequence to sequence models are also there. Or you can actually, start creating model from scratch with the help of drag and drop options of dropping multiple layers onto the canvas. So model building is interactive. Even if you want to go 100 layers deep, you can actually visualize how your architecture looks like, edit a lot of hyperparameters within this app without writing any code. Once we are done with that, you can analyze the network for how many number of layers has it got and what is the memory footprint looking like. And then you can actually, also, select to generate a particular line of code, which you can embed for model creation, and also the training options for training the deep learning model. Right. And then once we run this particular section of code, you would see that the deep learning model training shows you how your losses or the, residuals are getting converged. If it is not converging, then you may need to change your architecture, but you get this interactive feeling of how your model is performing on your data, and you get the proper metrics, R square value, RMSE value on the training data and on the test data. Right. Now, the next step is basically bringing this model into a larger, system model. So that is where I would like to show you in this application of the automotive, vehicle. We basically replaced the engine torque, prediction with the deep learning model, because that block was taking a lot of time. And once we have done that, then we basically, simulate this model in a much, much faster time. The same model which was taking us, good amount of time, we are able to save almost 2x to 3x, time with this particular steady state model that we have got over here. Right. So this is another example of, battery-based electric vehicle thermal management system, where actual simulation was actually taking up to, 3 minutes, and we got almost 6x benefit by integrating the same workflow over here. So that is what I had to say on a complex, ROM application in an actual high fidelity passenger car environment. Now I would like to ask Kaustubh or Manish if you have any follow-up questions on this particular segment.
Yes, surely. Thank you for a very insightful presentation. You gave a lot of case studies. My question is, what is the key trade-off when using ROM, reduced order modeling? And what do we sacrifice, and how do we ensure that it remains acceptable?
Right, that's a very interesting question, Manish, because when we are talking about reduced order model, it's important to understand, that these models are basically interpolation models. The amount of data that you generate looking at your system as an environment, and that is where I introduced the concept of design of experiments. You should know that which parameters vary as a designer or as a domain expert under what range, right? So for example, if you are looking at temperature in Indian conditions, you would go from something like 4 or 5 degrees in winter to almost 46, 47 degrees in summer, right? So your ambient temperature should vary in that particular range. And while you are working in different country, the same vehicle would have have different temperature, exposure. So it's important to understand whatever model you have trained, what is the data that you have generated, and extrapolation is where these models are likely to not give you, good enough results. Having said that, you had a question on, validating the performance of these models as being whether they are acceptable or not. So that is where the data that you have generated, the model that you have generated, you would have certain test cases where you would mention that given this volume of data and this kind of environment, I am expecting the model's accuracy to be somewhere around 95%, 98% with respect to the ground truth that my simulation model was generating. And maybe with respect to the other requirement on reducing the simulation time, you could have some criteria on how much speed up do you want on the simulation time to be cut down. So
Okay.
that would be my take, Manish, on that.
Thank you so much. And I would also request the participants to post their questions in the Q&A box. Back to you, Piyush. Yeah.
Yeah. So maybe Kaustav, here I would like to ask you that you have also worked with a lot of automotive customers and you have seen the deployment side of it quite a lot, where you have helped them deploy these models on embedded systems. So can you throw some light on what are the challenges with respect to the embedded system and how does the overall workflow look like? Kaustav, you're on mute, I guess.
Yes, yes. Thanks, Picho. This is a good question, good topic to discuss. Right. Okay. So we'll be maybe covering the embed AI topic. So maybe we also call it as a edge AI, on-board diagnostics, these kind of things, right? Maybe I will just first walk you through one use case, right, where is a good example to transition between the ROM to embedded AI, right? So this is, I think, one use case we work with the Mahindra. They wanted to develop a virtual sensor for cabin temperature estimation, right? But they had a actual physics-based model in GT power. So first we applied the ROM, where we converted the GT model into the ROM model, which is fast running, and then we deployed that ROM actually on the hardware. So we deployed that ROM, which is nothing but my machine learning deep learning model, on the hardware for the real-time temperature estimation. So it is combination of both. So embedded AI plus the ROM. Now, talking about edge AI or embedded AI, again, there are many challenges which normally our customers are facing, engineers are facing. First is nothing but the integrating the AI into the embedded devices, right? Because we have developed the AI machine learning in different ecosystem and our embedded or microcontroller is from different ecosystem, right? How can we deploy that easily on that third-party hardware? Second is the, since the many hardwares are having the less memory footprint, how we can fit those large deep learning machine models on those hardwares. Third thing, not everyone is master in writing a C code, right? Or writing a C or C++ code, right? Then from our machine learning model, deep learning model, how we can write or create a error-free code, right? It might be the CUDA core, it might be the C, or it might be the C++ code. Last, again, main challenge is that I'm getting very good accuracy of my AI model at the desktop level, right? But what is the guarantee? How can I ensure that I'm getting the same accuracy post deployment, right? So these are maybe the 4 different challenges. I will just try to address some of those challenges, right? Maybe by introducing you the different AI compression techniques, then how you can generate the error-free code, as well as maybe how you can achieve the real-time performance, right? Again, I'm just continuing with the same workflow, 4-bucket workflow, which Piyush has introduced in his session, in his talk, right? So data preparation, AI modeling, simulation and test, then deployment, right? Now, when we talk about the fitting the large models on the memory constrained hardware, right? I would like to introduce maybe one more bucket here, right? This is compression. So it provides, maybe the MATLAB provides some apps and functions. By using that, you can apply those compression techniques, maybe like pruning, quantization, projection, which will help you to reduce the memory of the trained deep learning or machine learning model without much compromising the accuracy, right? This is what we normally talk about, the compression techniques, right? So which will help you, maybe once you do that, maybe the deep learning model will be more memory efficient. It will be more faster as compared to our original models, right? So for that, maybe I will just I just have maybe this one slide. We have pruning projection, which is maybe normally we label it as a structural compression techniques, right? We are normally in pruning, maybe you normally maybe cut down some layers of the layer or some structural parts of your deep learning model, again, which will help you to reduce the memory. Projection, again, one of the IP technique of MathWorks, right? It is very similar to PCA. And we have the quantization, which is a data type compression, right? Where we convert the double precision data into the single precision data, again, to reduce the memory footprint. And then we normally go ahead for the microcontroller or the hardware deployment. So you can see here, maybe if suppose you have maybe 600 KB original model, you normally maybe compress up to maybe 300 KB. Again, you might expect a little bit drop in the accuracy, maybe 1 to 4%, but on the other hand, you are getting very much faster model, right? Faster as well as the memory efficient model. This is regarding the compression techniques. Now, the MathWorks provide the very unique automatic code generation framework, right? Where maybe in case you want to deploy the model maybe on the GPU, CPUs, or maybe PLCs, you can directly generate the code without rewriting the code manually, right? Suppose I have some deep learning model. These maybe the packages or the modules or toolboxes can generate the code, and you can deploy the code on the respective hardwares, right? Again, there are maybe two different kind of code generation framework. One is you can generate maybe the library-free code, which is nothing but the generic C or C++ code, that you can take that code to the respective IDE and integrate to your existing microcontroller or the embedded hardwares, right? Second, we also have a lot of hardware support packages. Suppose you are working on maybe NXP, maybe TI board, or maybe NVIDIA board. In that case, you can also generate the target specific code, or we also call it as optimized code. Where while generating the code, it will leverage the libraries of the third-party tool, and it will generate the target specific code. And you can go ahead and flash that code on the respective hardwares, right? This will be we normally call it as automatically code generation capability from the MathWorks side, right? And before now, I'm just coming back to the third pain point. That is how can we ensure that my model is performing well on my hardware, right? In that case, we normally talk about the PIL, that is the processor in loop simulation, where, like Piyush mentioned, once you train the model, you integrate the AI model to the system level simulation, and then you can maybe attach your hardware maybe through wire or maybe through Wi-Fi to your system. And in that case, you normally run your AI directly on the hardware. So the AI model will run on the hardware, on the actual hardware. Rest of part will be simulation. And once you do the simulation, then we can maybe do the profiling. You can maybe estimate what is the static dynamic memory on the hardware, what is the accuracy of model on my hardware, what is the execution time on hardware. This will give you confidence about your model's performance before going for the production deployment, right? So this is a good, I can maybe quickly show the video. So here I have, this is a battery SoC model, which I have integrated with your BMS and all the stuff. Then I'm choosing the support package, NXP, like I mentioned before. And then maybe you can do some configuration. And after that, you can maybe run the PIL simulation, right? So you can see here, this is my SoC output. So one is the true, which is nothing but the measured one, and the blue one, which is coming from the hardware. So my SoC AI model is deployed on the hardware, and I'm getting the output back from hardware to my desktop, right? So this is how you can verify the performance of your hardware directly on the hardware, right? Now, like I mentioned, maybe we have many support packages. If you go to the MathWorks hardware list, maybe you can mention, or you can see there are many hardware support packages. By using that, you can directly generate the optimized code, right? Okay, so in summary, maybe you can train the model in a MATLAB. You can create a ROM, virtual sensor, then integrate to the system level simulation and go ahead for the code generation. Or some people also might have question that suppose we have already built a model, trained model in Python, right? In that case also, in case you are working on maybe on the TensorFlow, PyTorch, or Onyx, you can import the model into the MATLAB ecosystem, and then maybe you can go for the retuning the model, doing some transfer learning, integrating that model to the system level simulation, and then go ahead for the code generation or the deployment, right? So I think this is maybe on the hardware deployment side. I hope maybe Piyush, this helps. Yeah, you're on mute, Piyush. You're on mute, Piyush, I think.
All right. Yeah, thanks, Costa, for sharing this. It was a really insightful, presentation on deploying AI to the edge systems, and particularly of interest was model compression techniques, because that is where we see a lot of hardware constraints while working with different industry verticals, not just automotive. Now, I want to switch gears a bit because nowadays we are hearing a lot about generative AI, agentic AI kind of systems, right? And people are doing, a lot of code generation or using large language models to basically advance their workflows. So we are seeing engineering at a pace that we have never seen before. Maybe if you can share some information as onto what MathWorks has to offer in the overall generative AI space, that will be really insightful, I guess.
Perfect. Yeah. Okay. So I think MathWorks have been investing or working on this space since a couple of years. I can maybe we just try to maybe again based on us, maybe our opinion is that the Gen AI is good, but it's not perfect, right? So that's why we are trying to combine the both capabilities together. Maybe some capabilities from the MATLAB Simulink domain as well as along with the Gen AI, I think. And also I will just try to maybe show you two different combinations of these offerings, right? So one is nothing but the agentic workflows. We have the agentic workflows where you can maybe connect the MATLAB Simulink with your own LLM models, your own platform, or you can do everything in the MATLAB by using the copilots, right? First, maybe I will just maybe walk you through the copilot, right? The MATLAB has this MATLAB Copilot where you can see maybe just like ChatGPT, you can see some chatbot inside the MATLAB environment. This is helpful in case you are very new to MATLAB and you want to do something in MATLAB, generate some code, or you have very heavy code and you want to understand code, you want to optimize code, and you want to go ahead with your next workflow, right? So just like I'm showing you, it's been there since the last 1 year, 25A. So I have this chatbot here. You can ask any question to the this chatbot, maybe for what are some different options for the smoothing the outliers. First of all, it will use some summary, technical summary, theoretical summary. Then also it will provide you the code. Now you can run the code here, test the code here, or if you are okay with the results, then you can maybe generate a .m script, MATLAB script out of this code, right? And this is trained on the MathWorks documentation, MathWorks community. So whatever you ask about the MATLAB Simulink, so it will answer you maybe with respect to theory as well as some MATLAB-based code, right? Second one option, maybe again, I'm asking you one more question that for what are the different options for the smoothing. Again, it is giving you some maybe some theory as well as some codes, right? In case you have already working in existing MATLAB script, also you can access the Copilot by using the Copilot in editor, right? So this maybe suppose you are writing some code, and based on the previous code, it will forecast some lines of code, right? Then if you're okay with that code, then maybe you can go ahead, or maybe you can maybe ask them to revise the code, right? Again, in case I have maybe some existing code is there, if you select that code, then you can see the access to a lot of different tasks. Maybe you can ask the Copilot, and maybe you can suggest or you can ask to do some changes in the existing code, right? Again, maybe put the voltage on the left axis and the SOC on the right. Based on your input, based on your prompt, it will recommend some changes. If you run it, again, it will apply some changes into the existing code. So this is a Copilot. So it is assistant to your workflow, right? Now, coming back to the second bucket, in case you want to have some more automation, in case you want to use your existing, suppose you are having access to existing MATLAB Copilot, or maybe, GitHub Copilot or Cloud AI, this kind of stuff, or you want to make it more automated way. In that case, normally you can go ahead with the second approach, that is the agentic AI. So here, normally we have introduced the MATLAB Agentic Toolkit, which is freely available. The first Copilot is a paid version, annual license, and in MATLAB Agentic Toolkit, it is available in GitHub page. You can download that. In this case, maybe it follows the MCP concept, right? It is nothing but the one USB which can connect your LLM with any app. For example, suppose you want to draft some email and send the email in an automated way to specific recipients. You can use that with the Gmail or Outlook. On a similar lines, we have also added the MATLAB Simulink in the same bucket, right? So you can connect your chatbot, your agentic platform with your MATLAB Simulink. You can give the prompt at the backend. It will open the MATLAB, run the create a MATLAB script, save the MATLAB script, as well as run the same successfully as save the results in the current directory. Everything will be automated in this work, right? I will just again show you one more example for that. This is my codex, OpenAI codex, and here I may be giving some question. For example, create and execute the MATLAB script that can load specific data, identify some right inputs, do some exploratory analysis, and do some visualization, right? So parallelly, it will open the MATLAB, it will create some code, then open the MATLAB, then save that code in a .m script, and then maybe it will execute the script, right? So I'm not touching the MATLAB. Everything I'm controlling from my codex prompt, what to do, right? Do the visualization, create some script, and so on. Also, I'm asking it to maybe write some MATLAB code to train some machine learning model. For some, here I may be training some machine learning model for the MPG predictions, miles per gallon predictions. And I'm asking codex to just show me the results. So these are the results of the trained model, the test results, right? So like I mentioned, you can do whatever you want by leveraging your own agentic platform, right? Perfect. Now, I'm just talking about some non-AI use cases, right? Okay, so we talked a lot about AI, Gen AI, but what are the use cases? Suppose you're working on maybe durability, CAE, 1D, 2D, 3D simulation thing. Which are the different use cases we normally see based on experience, which you can start working on from the next day, right? So these are use cases mostly inclined towards the automation, right? Maybe you have a lot of data from the simulation, how you can automate it, maybe by using some MATLAB app, how you can maybe generate some reports, triggers the simulations, run the simulations, analyze the reports, compare the simulation results against the test results, and so on, right? So again, we'll be sharing this slide deck with you. Maybe you can do some deep dive into the same. You also find a lot of links I added here, which can redirect to the documentation, tutorials, as well as some on-ramp trainings, right? Maybe so this is the last poll. Maybe I would like to raise this poll. Okay, so we have a very small duration of time, but we just touched upon different AI use cases in automotive. Piyush talked about the ROM use case, as well as I also touched the embedded AI and the agentic workflow. But let us know how maybe in case you want to have some deep technical session on specific topic, you want to do some POC by using some use cases which we discussed today, right? Let us know your feedback. Based on that, maybe it will help us to connect back with you to work on the specific topics, right? As well as I would like to ask Manish, in case Manish, you have any questions.
Yeah, surely. Meanwhile, I request audience, there are some audience questions and we will take some of them surely. So I will just request the audience to please make sure that you have the questions ready. And as we have announced, please also stay till the end because we have exciting lucky draw prizes coming up. So please please stay back till the end. Now, Kaustubh and Piyush, both of you, this was a wonderful presentation and really enjoyed both the presentations with a lot of case studies. And I would now request you both, you can take up this question, is how do I decide whether to run inference on device or on the cloud?
Okay. So this is very, so we see a lot of these sort of questions when we discuss with the customer, right? So once you train the model, normally we have high level, you have two options, whether you have to deploy on the edge or maybe on the cloud, right? That may be call you can take based on the applications, right? Let's talk about one use case. I suppose I have trained two models for battery. One, calculate the battery SOC, percentage of charging, and second, you calculate the battery SOH. It is the life of the battery. Now, suppose you want a very real-time estimation, for example, battery SOC. In that case, you can choose the edge. So the edge will help you to give the very instant estimation, very instant inference, because the edge has access to sensor data. It will clearly calculate the SOC, and then you have access to the SOC, right? So wherever you want, maybe wherever you want the very hard real-time estimation, hard real-time results, you can go ahead with the edge. Wherever you don't need hard real-time estimation, maybe for battery SOH. Battery SOH, it is okay if I want to trigger that model once a week, once a day, or maybe once a month. In that case, you can deploy those models maybe on the cloud. right?
Okay.
So in that case, maybe on the cloud. This is one criteria. Second criteria, depending on the memory size. If you have very heavy model, then it's difficult to deploy on the edge. In that case, you can deploy that model maybe on the cloud, right? So this is maybe one criteria to choose when to switch to edge or when to switch to cloud.
Yeah, SoC and
Yeah.
edge is preferred, but depends on the application and the data
Application.
size, as you said. Yeah, right. I have another question, and before we take the audience questions, is how is the MATLAB agentic toolkit different from general AI tools like generative AI tools like
Okay.
ChatGPT?
Okay, so this is also a good question. What is the differentiator? Okay, so this is based on the MCP. First is it is based on the MCP, which is called as Model Context Protocol. And in addition to that, we also added some skills from the MATLAB sibling sites. So those are nothing but systematic workflows to create a script, execute the script, and calls from some domain-specific MATLAB functions. Right? Suppose I'm giving some prompt based on suppose I'm doing some prompt, hey, create some signal processing task. Then, since we have added some skills, signal processing skills, it will only call those skills, and at the backend, it will only call the signal processing module or toolbox, and it will execute the task. It is nothing but the skills are maybe enabling your agents to behave like a MATLAB or Simulink engineers instead of just maybe generating the code, right? So it will benefit you in two different ways. One is nothing but it will reduce the hallucination because it will only execute that specific task. It will only call that specific toolbox. It will reduce the hallucination. Second thing, very important thing, it will also help you to optimize the tokens, right? Because right now it's okay, but once you start maybe widening the usage of the copilots, right? You will face the issue of the tokenization. So these skills are very helpful when it comes to optimizing the tokens, right? So Piyush, maybe you can add in case you want to add anything. Yeah.
I think you covered it well, especially on the agentic systems, and the skills are really powerful in bringing up the overall uses of tokens because as we see more adoption of agentic toolkits across different software platforms, one challenge that remains common is how do we determine or how do we get more deterministic results, and then the second is how do we limit the uses of tokens because AI, although it is doing a lot of coding job, it doesn't come for free, right?
Yeah.
I mean, especially the good models which is out there. Yeah. So I think with that, I would also like to, thank Pro Manufacturing Media team for inviting us to this particular webinar, hosting us, and giving us this opportunity to take your audience through reduced order modeling as well as embedded AI and generative AI kind of use cases. Maybe Manish, with that, we can move on to the Q&A segment.
Yes, absolutely. There are some very, very, very interesting questions. And I'll read one of them is I need to use this to control a motor with hardware suggested for 120 amperes and 13 volts. Is this possible? I am saying this a lot.
Okay. Costa, do you want to take it up?
Yeah. Just.
So I think this question came up when you were talking about embedded AI use case.
Yeah. So I need to use this to control the motor with hardware for TRPS. Yes. Yes. So I think this is very much possible. This is straightforward workflow. Maybe we also have the motor control toolbox, which can maybe bring the easy compatibility with the hardware and the Simulink model, right? I'm not sure whether you are using it or not, but maybe we encourage you to use that motor control toolbox. Also, this is compatible for the hill mill sil. It means it's also compatible for the hardware deployment, right? Maybe I can maybe just paste that link in the chat. You can maybe start using it. But again, if you need some help or some hands-on support from our side, maybe feel free to drop a mail to us. Yeah, maybe you can drop to Piyush or me. We can definitely help you on that.
And with respect to deployment of AI specific models also for motor controls, we have some good examples covering a variety of hardwares actually. So it will be better, Pranav, to get in touch with us so that we can give you more insights on how to basically use this with motor control block set.
Yeah. There's one more question we'll take. How can we implement ROM in CAE?
Yeah. I
Yeah.
can take that up. So for CAE applications, one thing is important is when you are dealing with CAD geometries, and basically you want to understand how the CAD geometries are linked up with a particular system response, then it is important to extract the features of a CAD geometry. So on this use case, we had recently worked with Hyundai Motors India Engineering, who also presented at our conference, a couple of months back. So we help them, extract a lot of geometrical features, almost 150 of them on CAD geometry. And then ultimately, also creating synthetic data, understanding how responses are changing, and then training machine learning and deep learning models for steady state and transient system response in order to track how these design changes are affecting your system requirements. So it is certainly doable, but we'll need to look at your use case. How does your geometry look like in CAE application, and then how can we generate the data and build a database on top of that?
Okay. Thank you. Thank you so much. There is one more question we'll take. I think we are close to our time, but we'll take this for safety control systems like braking or steering. How does MATLAB support formal verification of neural network behavior before deployment?
Yeah, so as a matter of fact, we have got the complete V-cycle support for using AI for certification kind of workflows, and on top of that, we have deep learning toolbox verification library, which comes as an add-on with MATLAB, which has these concepts of formal verification. And to give you a small example, let's say that when we train our deep learning models, it is doing good on your test data as well. But it will be encouraging to test these models when you add just the smallest amount of random noise to the data, let's say 0.5%, and see if the model is giving you the similar kind of results which it was giving you on the test data earlier. So this is one of the formal verification techniques. On top of that, we have got out of box detection as well, to give you more confidence where the model is not producing the right set of results, to stay compliant with answering where the model doesn't understand when your environment has changed from your training data set, right? So those kind of workflows are there in MATLAB.
Okay. I don't know whether we answered this, but I just wanted to check. I'm having a problem in selecting hardware suitable for MATLAB. Is there a FPGA with MATLAB support like that?
Yeah, so we have got HDL coder as a product which generates FPGA code, and DL HDL coder which converts your deep learning code into HDL code as well. So we do have support for HDL, code generation, and multiple RF sock boards are also supported when you're talking about FPGA code generation.
Okay. Okay, great. So since we are close to our end time, first of all I thank team from MATLAB, MathWorks to uh, partner with Pro MFG Media for this wonderful initiative. It was very insightful. I thank Piyush and Kaustubh both for a very insightful presentation. I know that there are many more questions which remain unanswered, but we'll take it up offline. And now comes the time when we announce the lucky draw winners. So the lucky draw winners will get uh, a surprise prize rather, and please keep a watch on your mailboxes. You will receive the gift. So I will announce the names first. B. Alaga Alagarusu from Ashok Leyland. Then congratulations, Dr. Maruti Khaire from Advik High Tech. We have Suman V from NSK Bearings, Subodh Kumar Saxena from Hero Motors, and Uday Sherikar from Orvia for Asia. And the last one is Rishabh Gupta from TMTL. I congratulate all the winners of the lucky draw. And I again thank Piyush Kaustubh for sharing their insights and experience. Thank MathWorks team for partnership with Pro MFG Media. And I thank participants for attending. And on your screen, you see a QR code. So this goes to our LinkedIn page. Please follow us on LinkedIn to keep a track of upcoming sessions as well as summary of today's learning. Thank
Manish,
you
I
so
just
much.
have one announcement to make before attendees drop off. We noted down, how many people had actually attended the session. We would like to tell you that we will send 1 month web trial access to you for MATLAB, and the presentation for this particular session will be shared within next 48 hours with you.
That's wonderful. Yeah, that will be very useful. Thank you, Piyush. Thank you, everyone.